and welcome to this lesson on ionic structure and properties. So write today's title and date in your books and we'll get started. Okay, so your starter today is to unscramble these key words. So pause the video while you have a go at that. Okay, you should have got ion, electron, lattice, and ionic bond. Well done if you got all of those. Give yourself a smiley face. Okay, so when we're doing ionic bonding, we've looked at this briefly before. What we take is a metal and a non-metal. And the metal wants to lose electrons because it's only got one electron, in this case for lithium, in its outer shell. And it's easier to lose one than to gain 7 to get 8. Then our fluorine on the other side, that's got 7 in its outer shell. So it's easier for that to gain 1 electron to get a full outer shell than to lose all 7 of the remaining ones. So what's going to happen is the electron from the lithium is going to transfer over to the fluorine to make lithium fluoride. Now, because the lithium loses an electron, that leaves it positively charged, and the fluorine gains an electron, so it becomes a negative ion. Those two can then attract to each other using the electrostatic force, and that's what makes the ionic bond. So when you're drawing this out, you get 1 mark for moving the electron across properly. Second mark is for putting it in square brackets, and the third mark is for showing the correct charges. So lithium as a plus and fluorine as a minus. Okay, if we then look at how that works on a bigger scale, here we've got a different compound, which is beryllium and oxygen. Okay, the beryllium has lost 2 electrons and the oxygen's gained 2. So the beryllium is positive, the oxygen is negative, and they attract to each other. Okay, and because they're attractive on all sides, they can attract other atoms, or other ions rather, on all sides. Let's have a look at this in 3D. Right, so this model shows sodium chloride. The greens represent sodium ions and the reds represent the chloride ions. And you can see that it is arranged in rows and columns to make a 3D structure. The chlorines are only ever next to sodiums, though. You don't get 2 chlorines together because they're the same charge, or 2 chlorides rather together because they have the same charge and they would repel. Equally, you don't get 2 sodiums together because they'd have the same charge and therefore would repel. So that's sodium chloride. Then over here we've got cesium chloride, which has a slightly different structure. So instead of being the rows and columns that you saw before, they are structured, it is structured slightly differently. So you've got your chlorides being the red again and your cesiums being the green. And you can see there the way it's structured is slightly different. But again, your cesiums are only ever next to a chloride and your chlorides are only ever next to a cesium. Okay, so a really important point there, the forces in the lattice that hold the ions together are very strong. That's because of the electrostatic bond between them. Okay, so key points here. Although ions form through the transfer of electrons from a metal to a non-metal, the ionic bond itself is formed through the electrostatic force between the oppositely charged ions. And it's that makes the giant ionic structures really strong. Right, your work, you need to go onto some assigned pages on Collins Connect and you need to answer these questions. You need to submit the answers to me either on Fronter or through an email, and you also need to do the quiz that I've set you on Collins Connect. Good luck.